Okay, so let's read the question again. First thing you should do, and also in the exam, please, in all these questions, you make sure that you understand the geometry. If no figure is supplied in the exam, try to draw it. Okay. If a figure is supplied which attempts, like this one, to be three-dimensional, try to draw a cross section so that you actually understand the geometry. Okay. And here, the geometry is pretty simple. If I take a cross section, I essentially have a cylindrical shell in the cross section which looks like an annulus. Inner radius is A and outer radius is B, and current is coming towards me in all the region between A and B, and the question tells me it is coming towards me uniformly. So I've already written it down. What's the current density? What was the definition of current density? Current divided by the area, current per unit area. So J will be I divided by the area between these two circles, which is pi b square minus a square. So there is no problem. Now I need to find the magnetic field in three different regions. Let me quickly state the simple ones. In the inner region, let's say for the first loop, B dot dl is exactly 0. Why? Because there is no current inside. For the third loop, which is B dot dl, right now all the current is getting through my loop, so it's going to be just mu 0 times total I B of R on the outside. If this is R, will be just the usual result for a wire, but that's only if R is larger than B. What makes this problem interesting is the middle region. So if I take an Amperian loop of radius R, that is on the inside between R, A and B. So for the second one, first of all, B dot dl, in the calculation of B dot dl, what's more important, symmetry or where the loop is going through? Symmetry is the most important thing. Okay, and symmetry was the same for the first loop, second loop, third loop. The symmetry tells me that B is parallel to dl, so this is just going to be 2 pi r times B magnitude again. No, nothing is different. Okay, but here for the second loop, what is I in? That's the hard part. Now, where is the current flowing? It's flowing only between A and B. But I'm not going to need all that current. I will need the current which is actually passing through this second loop. So, which region is that? If I actually try to cross hatch it, I need the region between my Amperian loop of radius R and the inner radii of A, right? So what's the current passing through this area? I in for the third. Well, what's the area of that region I've highlighted? Pi r square minus a square times j. So it's going to be pi r square minus a square divided by pi b square minus a square times the current. Alright? So I in apparently is what I found. Pi is cancelled. R square minus a square divided by b square minus a square. I. So what is b dot dl? it's equal to mu 0 times I in, so it's going to be 2 pi r. The magnitude is going to be mu 0 r square minus a square divided by b square minus a square times I. So magnetic field is going to be mu 0 I over 2 pi r for the region R between B and A. Now, the question thankfully just asks the magnitude of the magnetic field which we have found. What would be the direction of the magnetic field? Come on, this is a wire, right? I mean, it's maybe thick, but that's not going to change the direction of the magnetic field. Okay, inside the magnetic field will be 0, but otherwise, if the current is coming towards me, magnetic field will always rotate counterclockwise, just like the Amperian loop I have drawn, right? Any questions? No? Let's solve one more question. As you see, I'm going to attempt something three-dimensional again. So here I have a ring of radius r. Has a total charge Q distributed uniform. Oops. And it's on the XY axis. Ring is on the XY plane with center at the origin. You may think that I have some amnesia. I'm saying electric charge while we're obviously discussing magnetic field. So what's going on? What's the magnetic field in this situation? Zero, right? I mean, if charges are not moving, magnetic field is zero. There is electric field. And right now I said it's just electrically charged. I did not say anything else. So let's make this interesting. The ring is rotating with angular velocity omega as shown. Sorry? Find the magnetic field at point P. Let's say this is point P, which is at Z. Now, does everyone understand the geometry? So I have a ring on the XY plane, but it's charged electrically. Let's say that's it's an insulator which carries this charge distributed uniformly on it. So when I actually rotate the ring, what will these charges do? They will flow with the ring. Right? What would that create? A current. What would the current create? A magnetic field. So we have to do this problem in two steps. First, we need to calculate the current on this ring, and the second step is to calculate the magnetic field created by a ring of current. Alright? Good. So, let's solve this. So if I look at the system from the top, this is rotating like omega. Right, that's how it's rotating if I look at the system from the top. Good. So this is the x-axis and this is the y-axis. Can you tell me what's the current running on this ring? To be able to do that, I actually need to remember the definition of the current. What was our definition of the current? Current was the total charge passing a plane per unit time. Right? That's it. So let's take some point here, well, some plane. How much charge is passing? First of all, why are charges passing this plane? Because they are carried around with the ring. Okay? So current here would be the total amount of charge passing this plane divided by the time it takes for these charges to pass. Now, how much time would it take for all the charges to pass once through my point? It would be one period of rotation, right? That would be one period of rotation. If the ring rotates once, all the charge would have passed through my point once. So I would say it would be Q divided by the period of rotation. Now if I know angular velocity omega, what is the period? 2 pi divided by omega. So my current apparently is Q times omega divided by 2. Alright? Now the question is much simpler. Now I actually have a ring that carries current I, and I would like to find the magnetic field it creates at a point Z above its axis. And how am I going to do that? Let's try to do that. Right. And do you think we can use Ampere's law here? There isn't enough symmetry for Ampere's law. Okay. Ampere's law needs either an infinite line or a plane. So here we actually need to use Biot-Savart's law. So that's what we are going to do. We are going to use Biot-Savart. And for that, what am I going to do? I'm going to split up my ring into small sections. Alright? And that I will do by taking a small section that sees an angle d theta, which is at an angle theta. Alright? But now, again, I have to be very careful. Which way would be the final magnetic field point? And for that, let me also look at the system also from the side. If I take a cross section from the side, so let's say this is the z-axis and this is the y-axis, what would I see? I would see that there is a current going in at radius r, and at the opposite side there is a current that is coming out like this, right? Now, if I take two small points, two differential current elements, one on one side of the ring, the other on the other side, let's try to find out which way they would actually create magnetic fields. First of all, let's think about this guy here, dl. And here is my observation point. Which way, I use more colors here, which way is the small magnetic field created by this dl point? Remember what Bio and Savar told us? It will be mu0 I over 2 pi dl cross r hat divided by r square. So I need dl cross r hat. What was that vector r? It was from the current to the observation point. So dl is into the board, right? R is like this. So dl cross r is going to be perpendicular to the line in that direction. Alright? Should I do it again? Yes. Which way is dl? Remember, this is a side cut. dl on the right hand side is into the board. So dl cross r. R is the vector, the blue vector here. dl is into the board. I have the freedom to rotate my palm, but I am rotating it along the second vector. I close my four fingers. So here is my direction, which I translate to here. So it's going to be perpendicular to this blue line. Let me draw that in another color. So this is going to be dB, and I will call it dB1. How about the magnetic field created by the opposite side, by the small current on the opposite side? So it will have an r vector like this. Let's look at the case here. Which way is dl cross r? This time dl is coming towards me. I have the freedom to rotate my palm, obviously, but I'm going to break it if I do it wrong. Okay. So I'm turning my palm so that my palm actually faces the second vector. So I close from the first vector to the other vector. So it's going to be perpendicular to blue line and pointing in that direction. Alright? So that's going to be dB2. So which way will the total magnetic field point? The x or y components, the components in the xy plane, will cancel each other. So these two components will cancel each other, which means finally dB will actually point in the z direction. B will be B magnitude times k hat. Does that make sense? What was our rule? We had one more right hand rule. When I put my hand along a loop, my thumb pointed in the magnetic field direction, so it does also actually make sense here. Alright? You're looking so hopeless, I don't know what to say. There are too many right hand rules. No, are you happy? Okay, good. Maybe it's just 3 hours, one after another, that you're all feeling tired, but let's finish this. Now, so I need to calculate BZ, and for that I need to calculate what DL is. What's DL here? DL is going to be, DL magnitude is going to be R times D theta. Okay, that's very good. Then how about DL cross R? DL and R are actually perpendicular to each other, right? So dB magnitude is going to be mu 0 I over 2 pi. DL is R d theta, right? Divided by, now this is R, this is Z, this length is Z square plus R square, so this is going to be Z square plus R square. But this is dB1 magnitude. The expression here is dB1 magnitude. What do I need? I need the Z component, not the full magnitude. I need the Z component. So what's the Z component? If the angle here is theta, the angle here is also theta, so dBz is going to be dB1 magnitude times cosine theta. Or let's call it another angle. I have already called something theta. Let's call it alpha. But cosine alpha is clearly R divided by Z square plus R square. So this is going to be mu 0 I over 2 pi R d theta divided by Z square plus R square times R divided by square root of Z square plus R square. So this whole thing is going to be mu 0 I over 2 pi R square d theta divided by Z square plus R square to the 3 halves. Right? So if this is dBz, what's the total magnetic field Bz? It's going to be integral dBz. It's going to be integral mu 0 I over 2 pi R square divided by Z square plus R square to the 3 halves times d theta. And my integration will go from, it will start from 0, it will go all the way through the ring, it will go to 2 pi, okay? And how am I going to evaluate this terrible integral? It's not a terrible integral. Nothing actually depends on theta. All of these are constants. Okay? And you would be amazed how many students just give up at this point. You know, like if you ask such a thing in an exam, they're like, horrible integral, how am I going to evaluate this? And just give up. So, actually, this is the easiest integral in the world. 2 pi R square Z square plus R square to 3 halves. And my handwriting is getting worse, so trying to at least make these tools nice. Integral d theta from 0 to 2 pi, which is 2 pi, which cancels with 2 pi here. So Bz is mu 0 I R square divided by Z square plus R square to the 3 halves, and now I made a mistake and nobody warned me. Tell me. Is this the Biot-Savart law? Cross product is right. Mu 0 I over 2 pi or 4 pi? It's 4 pi, right? You're 1 week away from the exam. And you don't know Biot-Savart's law. That's not going to be well. That's not going to end well if you don't learn it, okay? apparently that's how the magnetic field behaves on that as a function of z. I'd like to plot the magnetic field as a function of z. What does it look like? Where is its maximum? When z is equal to 0. Does that make sense? Look, I have a loop that has a current. The maximum does make sense. That's where everything adds up. Okay? So the maximum is at the center of the loop. That's why when I had many loops, when I added them, I got the uniform nice field of a solenoid. Alright? So the loop magnetic field is maximum at the center, and I can't get my maximum to the center. Okay. And it's always in the same direction. Okay, it's always found by the direction by putting my 4 fingers onto the loop and my thumb points along the magnetic field direction. Right? Good. Any questions? Now, I think I have pretty much covered all the stuff that's needed for the exam. Okay, so we're actually done with what we need to learn. But we have 3 more lecture hours this week. In one of them, in the last one, on Wednesday, I'll actually do a review of what we have learned between the first midterm and the second lecture. On Monday, I will solve as many questions as possible. And I urge you, please, go through the solved quizzes, but also go through the assigned problems. Do you remember these selected problems? I'm sorry, the selected problems. The list of selected problems is still on the Moodle server. Attempt that. Good luck in the exam. I'll see you on Monday. Anyways, yes? No.